To solve dynamic problems correctly, we need a consistent strategy. We will work on a few examples on Newton's second law in this lecture. Let us recall the concept of free body diagram. A free body diagram is a diagram that represents the object and the forces that act on it. We also need to build proper coordinate system. In dynamic problems, we apply Newton's second law to objects on which the net force is not zero. These objects are not in equilibrium and hence are accelerating. We need to break down any forces that don't line up with your axis into their x and y components. For the objects we are investigating, write out Newton's second law for each axis. The net force in x direction equals to mass times acceleration in x direction. The net force in y direction equals mass times acceleration in y direction. Now you have a system of equations. The rest is algebra. Solve for your unknown target variable. Systematically, after we have identified the problem to be a Newton's second law problem, we need to do the following. First, set up the problem. First, draw free body diagram for the object, illustrating all the forces acting on it. Then, establish a clear x and y coordinate system. Then execute. Decompose each force into its x and y components according to your axis. Applying Newton's second law by writing separate equation for each axis. Net force in x direction equals to mass times acceleration in x direction. Net force in y direction equals mass times acceleration in y direction. Finally, solve the system of equations you have created to find the unknown variable and check that your answer is reasonable. So let's start with the elevator example. This time, a 740 kilogram elevator accelerates. So when we see this keyword accelerates, we know it's a Newton's second law problem. Accelerates upward at 1.1 meter per second square, pulled by a cable of negligible mass. Find the tension force in the cable. So we have identified this is a Newton's second law problem. So the next thing we need to do is draw the free body diagram on the elevator. There are two forces, one from the cable, one is the weight of the elevator. So we have net force on the elevator equals mass of the elevator times acceleration of the elevator. Net force is the sum of tension and weight equals to mass and acceleration. Okay. In principle, we need to build our coordinate system. So let's do that. X coordinate, Y coordinate. Pay attention and think about this. What's the direction of acceleration? What's the direction of tension? What's the direction of weight? It looks like everything is in Y direction. So we can focus on the Y direction. The tension is in the positive Y direction. Weight is in the negative Y direction. This is weight equals M-A-Y. Acceleration is in the Y direction as well. Looks like acceleration is pointing up. Given by the problem, right? Accelerates upward. So we can solve for T. And the problem gives us what's the mass. So mass is 740, g is 9.8, upward acceleration is 1.1. Put everything together, we find is 8,100 Newton roughly. Okay, and we also get this tension equals to mass times g plus a. It works, seems, hopefully this works for any acceleration. So we check a few special case. What's happening if a equals 0, which means the elevator is doing uniform motion, aka constant velocity motion, which gives us t equal mg, which is exactly what we learned when we're doing Newton's first law problem, right? When the elevator is doing constant velocity motion, net force is 0, so tension exactly equals weight. Okay, now if ay is negative g, which means the elevator is going down with acceleration g, tension is 0. Elevator is doing free fall, which is also reasonable, right? So we are confident we got it right. The second example, a worker with spikes on his shoes pulls with a constant horizontal force of magnitude 20 Newton on a box with mass 40 kilogram resting on a flat frictionless surface of a frozen lake. What's the acceleration of the box? So we need to draw a free body diagram as well. Now, fortunately, it looks like the problem already drawn it for us. So we have tension pointing to the right, normal force pointing up, weight pointing down. And this is our x, this is our y. So the net force in one direction has to be 0 because the box doesn't have any movement in y direction. Hence, acceleration in y direction has to be 0. The net force in the x direction is not 0. It has a net force. So what's the net force in x direction? There is only one force. There's only one force in the x direction, which is tension, which is 20 Newton. So Newton's second law tells us net force in x direction equals to mass times acceleration in x direction. So acceleration in x direction equals net force in x direction divided by mass. 20 divided 40, mass is 40.5 meter per second square. Okay, one last example. Suppose a block with mass m is on a frictionless ramp. The angle between the ramp and the horizontal axis is theta degree. What is the acceleration of the block along the incline? Is the net force on the block going to be 0? More than likely no, right? From our everyday experience, the block is going to slide down from rest, so there has to be some acceleration. So we can kind of make a conclusion this should be a Newton's second law problem. So the first thing we do is free body diagram. What are the forces acting on the block? We should have a normal force from the ramp, weight, okay, and then we build our coordinate system. Because the block is moving along the ramp, so let's choose the direction along the ramp to be x, this to be y. Okay. Is there any movement in the y direction? No. So y direction, no movement. Ay is 0. Net force in y direction is 0. X direction, accelerating, right? So ax is not 0. Net force in x is not 0. So we need to find out what's this net force in the x direction. So I will ask you to draw this on a paper and then maybe turn your paper, draw this free body diagram on a piece of paper. Turn your paper clockwise by angle theta, and then what would be the free body diagram looks for you. So after you turn, you should have your x become horizontal, your y become vertical, but then what would be the direction of your normal force? Your normal force should still be in y direction. Was the direction of my gravity? Now it should be this angle. And with geometry, we can argue this angle should be theta, because this one add up to this one give us 90. This one add up to this one give us 90. So these two angle has to be exactly the same. Okay, so which means my mg is pointing in this direction in this x and y coordinate system. So compare those two. So what I ask you is draw this on a piece of paper, turn it clockwise with theta degree. You will find a much easier to understand free body diagram. So as we discussed, net force in y direction is 0. Net force in x direction. Normal force doesn't have any component in the x direction, only mg. And then if you look at this is a rectangular triangle. This is hypotenuse is my mg. This is angle theta. X component of mg is the opposite side of this triangle. So it's mg. If you want to find the opposite side, you need to use sine theta. So this is the net force in the x direction, which turns out to be the all net force acting on the block. So the acceleration of the block is given by solving this equation. So we're going to divide a m on both sides to find out ax. Turns out it's just g sine theta. Okay, we can also try to evaluate and assess whether we got the right result. What's going to happen if my theta is 0? Ax is going to be 0. Does it make sense? So if the angle of the ramp is 0, there's no acceleration. I think it makes sense. What's going to happen if my theta is 90 degree? Sine 90 degree equals 1. If the ramp is 90 degree, then this block is going to do free fall, right? Yeah, totally makes sense as well. I hope those 3 examples is helpful for us to understand how to solve Newton's second law problem.